All right, well, thank you, everyone. I'm trying to keep it a little bit light and fun today. So yeah, I want to talk a little bit about going from AI software engineers, or maybe from software engineers in general, to AI knowledge workers. I've been in this area since 2017, when I switched from programming languages to using AI to increase developer productivity. At Meta, we had quite a big group of about 100 people where we were building tools to increase developer productivity, system efficiency. And at that time, we were trying to, we thought that code has special structure, it is tree-shaped or maybe graph-shaped, and we need to build custom models to kind of capture the semantics of code. And so we had as I said, 100 people with PhDs in machine learning to do this stuff. We wrote a paper about it, got a best paper award, and then ChatGPT came out, and then I realized these general purpose models kind of beat all the special purpose models that we have. My group was eliminated for a good reason, because it all crap, all these 5 years of work in vain. So that's where we are. But then I really realized that targeting traditional developers is the wrong thing to do. And why is that? So let's take a step back and think, what is the essence of computer science, or maybe what are we doing, right? What is our role in life? And what is what is the ultimate goal of programming? And I think whatever it is, it all boils down to free humans from mundane, repetitive tasks. And if you look at here on the left, this is what we as academics and computer scientists like to do. It's a little bit like navel gazing. We're building tools for each other. We have machine code. Let's build an assembler to make that easier. Let's build a compiler, and it's all just reinforcing with ourselves. But ultimately, of course, what we want is some business user using Concur, and maybe you are that business user when you kind of come home at the end of this conference to submit their expense report. So things like Concur are the ultimate tools that we as computer science are aiming to build. But of course, everyone that has ever used Concur will know that this is a piece of shit. But I don't know, 50, 70 years of computer science have yielded something as shit as Concur, right? So clearly we have failed. We got we got an F, not even something for effort. We completely failed as a group. So, and the sad thing is that people pointed this out years ago. In the Humble Programmer, 1972, Dijkstra mentioned this. But even in 1968, there was the famous conference where the software crisis was invented, pointed out. And it just really saddens me that we've been talking and writing papers and doing everything for so long, for decades, and still we are not able to write useful software for the end user. Now let's take another step back and look at something that has been successful, and namely that is hardware. If you look at hardware in those decades, thanks to Moore's law, hardware has gotten bigger, more transistors, the hardware has gotten faster. And now that faster hardware has enabled us to write more powerful software. That more powerful software enables to build faster hardware. And this is I think, a virtuous cycle that has driven the industry forward. However, on the software side, the things don't scale. That's where we have Weird's law. It's like, the faster the hardware becomes, the more bloated software becomes. So while this loop it's a miracle that this loop is still kind of like going on, because we're fucking it up on our side. And so what do we do? Well, I think what we're trying to do is we're trying to fix it by introducing process. We're doing like crazy things like Agile, Scrum, and there's whole conferences about it, like, about software engineering and processes, and it's not working. The problem is transistors scale, but humans do not. I think there's a lot of professors here, and I don't know how many PhD students you have, graduate students you have, like maybe 5, 10, but if I say, like, let's double that every year, you'll say, Erik, you're crazy. That's impossible. All right? If you can work in industry and you say, let's increase our teams, let's double it every 18 months, you say, fuck, that's crazy. That's impossible. All right? But on the hardware side, that works, right? We can just keep on pumping out more transistors, and the hardware keeps getting faster. So the real problem is humans. Humans don't scale. Humans are the problem. And what we need some kind of Moore's law, but for software. And I think the only way, really the only way we can get there is by getting all the humans out of the loop. That's the only way we can make software scale. That's the only way we can ever hope to get something better than Concur. So that's like after my team was dissolved, that's what I kind of concluded. We have to eliminate developers from the loop. And I must say, I'm super sad when I see companies, like startups that work on AI suites, getting so much funding, because that's just throwing money into the garbage and setting it on fire. It's like building tools for blacksmiths. It's it's just throwing money down the drain. What we need to do is we need to say, can we build software without developers? That is the only way we can create a Moore's law for software. All right, so how do we do that? Well, people have tried with low code, no code. And I don't know if there's anybody here that has ever tried low code, no code. I really don't understand how anybody can write applications with that kind of crap. It's like you got you drag and drop stuff together, and then you have to kind of click, and then you end up in some weird JSON thing that has some weird internal programming language that is completely ill-defined, all composed out of strings. And if something goes wrong, you get stuck. The only thing you can do is can throw the whole thing away, start from scratch. What's even worse is that I'm not a big fan of version control and things, but they kind of are useful. But these tools cannot leverage any of the tooling that we have built that might be useful, right? It's a completely separate world. And I'm really, honestly, just completely baffled that anybody can really write things with these low-code, no-code tools, especially people that are not developers. But maybe I'm just a really bad developer. So yeah, these low-code, no-code things, they're really low-level imperative code in disguise. They're not defined in terms of the domain abstractions of the users. Typically, the kind of primitives that you have are just call some REST API with some boxes and arrows. They're not leveraging any tools. You cannot debug, you cannot put breakpoints. And I mentioned this already, but the programming languages that are below them are the weirdest I've ever seen. This is like Clown Town, Amateur Hour, and maybe I think the people that wrote this don't even realize that they're creating a programming language. I think there's way too many product managers and crap people out there that have no clue what they're doing, that are involved in building these products for normal people. So these guys should also kind of get away, right? So no developers, no product managers, free the end user. Free the end user using AI. Now, what we have been trying to do as our field is like, oh, let's use AI to do natural language to Python or SQL. And so there's like whole kind of like, you know, competitions where people get like, you know, like fine-tune models or write prompts to generate natural language or like from natural language, generate SQL, or what is a Sui bench and so on. If you look at the code that gets generated, it's just clown town. Nobody is able to understand that. Nobody is able to maintain this. So we're just creating noise, we're creating garbage. So I think this is a dead end as well. So I hope I don't insult anybody here, but if this is what you're doing, I think you're wasting your life. So here's the real problem. If I look at traditional language, first of all, they are designed for developers to write, and maybe not even for developers to write. It's more for von Neumann machines to execute. We want to say like, oh, my language is designed for other humans to read. It's wrong, right? All these languages make compromises such that we can make them run fast on von Neumann machines. The other thing is the semantics are too complicated to mechanically reason about correctness. I visited Krista Lopez at UC Irvine yesterday, and she has been like, you know, doing some interesting work to use an LLM to generate Daphne and to generate like loop invariants and pre and post conditions. And oh boy, like I grew up in the Netherlands, Dijkstra country, and we had to do that kind of shit, loop invariants, pre and post conditions. And it's like, you know, like 50 years later, and it's still as painful as it was back then. If you have to do anything more complicated that deals with arrays, you have to like write all kind of weird formulas with indexes and so on. And even the simplest programs, like, you know, the specification is much harder to write than the actual code. So even with AI, I don't think this scales. And the reason is, I think, that the languages are too complicated. And the languages are not designed with automatic verification in mind. And so what do? We write tests and so on. But of course, tests are not really good to create correct software. And I will tell you a little bit more about that later. And then the same thing as I mentioned for these low code, no code. Languages like Python are general purpose. They're not defined in terms of the domain abstractions of the user. Haskell people will say, but we can write DSLs in Haskell, but then you're stuck with Haskell and like people's brains are going to explode. And then the last thing is that most programming languages require complete programs to execute. So you have to create a full program with all the dependencies, then you have to compile it, run it. Of course, I know people here are trying live programming and whatever, but I think the majority of the programs, it's like a very slow compile, edit, run loop, which is not great for the use case that I will show in a few slides. So traditional languages also just disappearing. If that's your job, forget it. Better look for something new. All right. So why do I say that testing in this new world is kind of useless? Well, people talk a lot about AI safety in the abstract. Oh, the AIs are going to escape, they're going to do bad things to us. I can go to the library and get a book how to build a bomb, but if the model tells me, oh, this is really bad. I think this is all very abstract. but we forget what is the concrete danger. Everybody that here has got, like, done code reviews, you know that if you don't want to have any kind of like comments from your reviewers, you just submit really big pieces of code that are really complicated, and then people will just say, okay, sure, I accept it, right? So now imagine that the model wants to do something sneaky. They want to put some backdoor in your code to send information back to some nation state. So what this model will then do, when it generates code, it will generate really complicated code, and so nobody will actually look at the code and say, oh yeah, it's okay. And the other thing, you can say, oh, but now we can have the model generate tests. Of course, the model will not generate any test that exposes the backdoors. Right? And so I do think that if we're going to rely on models to generate code and generate tests for us, it's really dangerous if we rely on traditional mechanisms to understand that code and to make sure that that code is safe. Now, if the end user is going to generate code using a model, they don't even understand what tests are. So my guess is that, or my thesis here, is that formal verification, automatic formal verification, is the only way forward to create safe AI. So if the model is generating code, it should also generate a proof that that code is correct. Of course, this is not a new idea. This is proof-carrying code, which was invented in the 90s. But I think time has come to get, that proof-carrying code will finally become useful and practical. And the way to make it practical is to design the language such that it's amendable to formal verification. So you have to keep the language simple as possible, such that you have a chance to do automatic verification. And with Python or C++ or Rust, all bets are off. You're not going to make that work. All right, so what am I proposing? Well, again, this is some old idea from the late 80s. And this is the programmer's apprentice. And I just replace programmer with knowledge worker because we're going to eliminate programmers. And so the idea is to provide every knowledge worker with an apprentice, a computer program or an AI that will help them do their job. And now I really like the word apprentice, and I don't like the word assistant or agent or co-pilot, for the following reasons. If you think about assistants get it feels like something that's assisting you with existing processes. And if you look at a lot of the big tech companies today, Microsoft, GitHub, Google, what they're trying to do is they're trying to add AI to the existing tools. So Microsoft is adding Copilot to Visual Studio. Why? Because they want to keep you to use Visual Studio and they want to keep you doing AI. But that's not the way forward, because what we want is we want to build new tools. We want to create a new world that is AI first. So I do think that these co-pilots are holding us back. And if you think about an apprentice, this is something that learns with you, that you have an emotional connection with. And so I really prefer this notion of an assistant. Now then, there's two things that I think you need to create a good apprentice, and that is search and code. So a lot of these if I look at these AI suites, they don't bring in shared context with them. So if you're employing an AI suite into your company, that agent needs to understand the context, right? It needs to understand what are the coding rules For example, at Meta, nobody writes code comments. And now if you bring in like a SWE assistant or a copilot that's going to write code comments in the code, it's just like looking kind of crazy. It also needs to understand what are the special libraries and so on. So there's a lot of context that needs to kind of come in. And that's like, you get that via search. And I'll call that like you need the nouns. You need the nouns to get like understand where you're coming from. And then the apprentice needs to be able to do tasks. It needs to get like perform actions. And these have to be domain-specific actions that are kind of like specialized for the user. And let's call them verbs. And now if we have nouns and verbs, then we can create sentences. And this is how the apprentice can work. And the way I envision this is that for every person, over time, the apprentice will create like a completely person-specific language of verbs and nouns. Think of like, if you would take A/B testing to the extreme, and like, that everybody's like applications would completely morph via A/B testing to the thing that's optimal for them. Of course, the big tech companies don't want you to do that because they want Instagram to look like Instagram for branding. But maybe I want my Instagram to look completely different from Gilad's Instagram. I don't even know if he uses Instagram, but so then that's easy. But anyway, so I do think that a lot of this kind of like the big tech is holding back progress in this area. All right, so let's like dive down now a little bit. So what I've been working on is two things. It's a language called Universalis, which is a language, and Automind, which is a runtime. And these are kind of like a runtime and a language designed for an AI-first world. And it's done by kind of like, I think, an interesting analogy. So first, let's kind of think, what is an LLM? Right, so the way I look at an LLM is kind of a database of compressed world knowledge. So for example, I can ask the LLM, what is REBASE? And stored in its weights is the knowledge of what REBASE is. Namely, in Git, REBASE is something that kind of like, that lets you combine a series of commits in some way. So that's a kind of like LLM as a database. Now, and so think of that as ROM, right? The weights of a model, that's like a ROM read-only memory of a computer. Now, let's ask another question. Like if we want to say, what's the current temperature in Pasadena? What we can do is we can put that fact in the RAM, in the context of the model, and then we can ask the question, and now the model can look up that fact in its RAM, in its context, and give us the answer. So context, the input context of a model, is very much like a random access memory. Now, this is maybe a little bit crazy. If you look at RAG, you've probably heard of RAG, Retrieval Augmented Generation, that is exactly like virtual memory. So if you ask, what is the REBASE conference, what the implementation around the model will do, it will go and search in secondary memory, get the facts, put it in the context, and then have the model answer the question. That's exactly what virtual memory does, right? You get the right information out of secondary storage, put it in RAM, such that like your program can access it. So RAG is just exactly the same as virtual memory. So do you get the feeling? These models are not that different from traditional von Neumann machines. There's like a one-on-one mapping for every concept that we know into something in this new world. Let's look at another thing, tool invocation. So say that we want to say, what is 100 Fahrenheit in Celsius? Because I live here now for 25 years, I still have no clue how Fahrenheit works. So if you ask the model, what is 100 Fahrenheit in Celsius, you will see that it gives you the answer, and then there's this little thing here. If you click on that, you see that it has executed a piece of Python that does the computation. Now I can go off on another complete rant about like how is it possible that Python surfaced as the preferred language for these LLMs. I feel super sad about that, but hey, it is what it is. But anyway, so this like these tool invocations, that's like the instruction set of this neural computer, right? It can execute things. It can take data and produce new data. Now there's one rabbit I need to pull out of my hat, because I want to get if we have a neural computer like this that has ROM, RAM, virtual memory, instruction set, we need to have like an assembly language, an internal language for that kind of machine. And in order to do that, as I said, like I need to pull one rabbit out of my hat, and that is to model instructions as predicates. And the reason I do that is that these instructions or these kind of tools can be another call to another LLM. This is what people call multi-agent systems. I find that kind of like amusing, because if you write a Java program that uses 2 objects, you're not saying I'm writing a multi-object program. But if you write a system that uses 2 LLMs, people say, oh, I'm writing a multi-agent program, look how cool I am. It's just fucking insane. Anyway, let's pull this rabbit out. How long do I have?
10 more minutes.
10 more minutes, great.
Including question time as well.
Good. So yeah, so let's pull the rabbit out of the hat and say, tools are relations. So think of this like I have like a relation convert Fahrenheit to Celsius. I have a relation file between file and content, between city and weather, or between like a prefix and a prefix where I predict the next token. If you model these things as relations, you don't need monads either, right? Because read file content, the next time I read the file, the content might be different. So you don't need like, the IO monad. It's just like a non-deterministic thing here. All right, so that's tools as relations. And now, code generation, generating these programs is really just like branch prediction. If you look, what does a branch predictor do in a traditional CPU? Given the sequence of instructions executed so far, it predicts the next instruction. Now, instructions, we've replaced instructions by predicates. So given a conjunction of predicates, what does the LLM do? It generates, it infers the next instruction, the next predicate to call. And so, really, generating these programs as sequences of predicates is just the same as branch prediction. So the LLM itself is like a branch predictor in the traditional computer. And then chain of thought, which are sequences of tool calls, is really the Mentalese or the internal language of LLMs. So the primitive tools are facts, and then you can chain these things into larger goals. And then just like in Prolog, what you can do is you can give a name to a sequence of clauses, which becomes a horn clause, and that creates a new verb in the vocabulary, and that's how you build these domain-specific vocabularies. So derived tools are horn clauses. So like I know if I have tools to get the geocode of a city, to look up the weather at weather.gov, and then to get something from a URL, I can now define the predicates to find the weather in the city just by the conjunction of these tools. And this is what the model will generate for me, given a natural language query. Some people that like fancy words say, this is neural symbolic computing. I think it's just freaking generating Prolog from natural language. Now, you can ask yourself, do I really need the full power of Prolog? And the answer to that is no, because in Prolog you have logic variables because you want to run things backwards and so on. In this case, I always execute things from left to right, so it's really more like attribute grammars where things just flow. And so in the implementation, you don't need logic variables. All right, summarizing, LLMs are neural computers, and here's the the mapping. I think this is pretty neat. So everything maps one-to-one. And then there's one more thing. As I said, I need to keep the language simple. And in Prolog, people, if you want to do repetition or so on, that's typically done using recursion. But I don't want to have full recursion in the language, because otherwise it becomes too hard to reason about. So what we do is we just add support for bulk operations. You can map implicitly by lifting predicates from the elements over values or over lists. And I add monoid comprehensions, just say SQL to it, such that all the recursion is captured in these special operations. So let's give here an example. And then the other thing is that the programs are embedded in an explanation. So if I ask a question, given a set of players, select the best team for the next World Cup soccer. I'm using, instead of uppercase letters, I'm prefixing variables with @ and now the model will generate something that looks like natural language, that has inside it these little snippets of Prolog, but really this is just doing group by and aggregation and so on. So what is my vision? My vision is to build the next Sun microsystems for the AI era, right? Because not only does the virtual machine map to the virtual machine of the past, but you need the complete ecosystem as well. So it's write once, run anywhere, prompt once, run anywhere. So this my runtime extracts over the different LLMs, and of course you need at some point some repository of facts to do code sharing and so on. But I think instead of having a measly developers, we eliminate them, and suddenly we get a lot more users. Let's dive now a little bit into the implementation. The implementation is typical multi-agent thing. So in order to, when something comes in, there's models that look at the outputs of models and do all of complicated things. In order to do this virtual memory thing, this RAG, you need to deal with documents that have structure. So what I do is I parse documents into ASTs and then index them based on the ASTs. I've never written so many recursive descent parsers in the last few months. And then I accidentally reinvented intentional programming because I was trying to make the model generate concrete syntax, but that turned out to be really hard. In the demo, you might see this if I have time for a demo. But then the models came out with guided generation, where you can give it a schema of JSON, and then it will generate the output according to the schema. So what you do is you just define the JSON schema for your AST, and you have the model generate AST, and then I print that into user-facing syntax. I generate Kotlin for execution, and then I generate Daphne for formal verification. So let's do the last few minutes to talk about verification. And this is my new slogan: bugs don't vanish with tests, only proofs ensure their absence. And so what we want, what I'm doing is I'm leveraging Daphne for correctness and safeness. So if you ask a question, and this is a whimsical example, right? So I have an apple costs $P, the price is raised by X%, how much does an apple cost now? So this is a question. The model will generate here a program that gives the answer. Now what you can do is you can ask the model as well, what is the precondition for this code? And then the model will generate a precondition. And since it says here that the price gets raised, the model infers that, oh, the price of the apples must be positive and the percentage must also be positive. All right, so this is not like the kind of precondition that you would have in traditional coding. It's more for something that the kind of normal user said, oh, this is kind of reasonable assumptions if I ask this question. Same thing here is the post condition. Often when you write like Daphne or you use pre and post conditions, the post condition is just another phrasing of the actual algorithm. So in this case, the real post condition should somehow redo this computation, which is nonsense. Because really what the user wants to know that the new price is greater than the initial price because I've raised the things with a positive thing. So instead of having full correctness, you just want to have like, something weaker that gives the user the sense, oh yeah, this is reasonable. And so that's, I think, still something that I'm investigating, where you don't want to have like full correctness, but you want to have something that gives the user a sense that the code that is generated is reasonable. And of course, if it's really critical code, then you want to turn up the dial to get full correctness, but in most cases, this is fine. All right, I don't know if I have time for demos, but maybe it's time for some questions.
Yeah, let's thank the speaker. We are running out of time, but let's take a few questions.
Yeah.
My question was, could you show us a demo?
I can show you a demo. I'm happy to give a demo afterwards. I think I have time for it, but yes, I have this thing up and running. It's not like like vaporware. It's right here on my computer.
So very thought-provoking talk. So I'm not sure I agree with your analysis of why hardware scales, and I think it has to do with a difference in how we specify problems. I mean, hardware teams are actually pretty complicated. There's thousands of people that work on CPUs. I think they have very good specifications, and they have like the ability to break down problems recursively and to have like input-output specifications. I think the problem in software is that we can't make up our minds. We don't know what the layers should be. You showed JVMs in your diagram of things. Those have gotten a lot faster over time because they have very constrained input and they have a very clear job to do. And I think that part of the problem in software is that we're not very good at defining what the jobs of different pieces are. So I think it really is a specification problem too.
Yeah, so maybe like we're violently agreeing, because I think we need to constrain our language that we can like express our code in such that we can reason better about it. But I do also think that the scaling of hardware that I pointed to is that I can I can cram twice as many transistors into something, and it will go maybe twice as fast or become twice as powerful. I cannot just cram twice the amount of developers on the problem and then expect that it will be solved twice as fast, unless you use Agile, right? That's like twice the work in half the time. But I can walk on water and turn water into wine as well. Right, question back there.
Thanks, Erik. Thought-provoking talk. So I guess my question is that the details of the vision you're pursuing is quite different from what a lot of the sort of major labs are doing. So the target is the same, which is knowledge workers and not programmers try to sort of make their lives easier. But I think especially with things like say anthropic computer use and other such demos, the vision that they're following is that for a lot of tasks, there is no program to be written. Like if I want to get a bunch of email addresses off, say, LinkedIn, I have no idea how to write that code, and no expert could even do that. Instead, it's better to just have a model directly interacting with the computer and doing that. So it's sort of not just eliminating programmers, it's actually eliminating programs as well, I would argue.
That's a very good question, and I would say what I'm proposing is not that far off from what they're doing, because in some sense, when I ask this kind of the thing that can kind of click on the website to do something, that is like a verb, right? So that is the thing that I want to achieve. Now imagine that I want to do another thing after that. Then I want to give that a name too, and now I want to say combine these two things. So I think the kind of being able to kind of automate certain part of the things is only the first. That's the leaves of the things. But now, if I want to reuse that, if I want to do it again, you don't want to kind of rephrase it again. So that's where you build this domain-specific vocabulary. So I think they are kind of mutually enforcing. It's not either or. So these are the primitives. And again, what I mentioned in the beginning is like a lot of the things that we see, the primitives are not in the kind of realm of the user, right? If you look at low code, no code, but these things, like if I can just tell it, like go and do this and it will click, that's at the level of abstraction of the problem domain of the user. But now you want to capture that and then kind of compose above that. All right. Thank you.